Welcome to Module 3 of Digital Signal Processing. We have just seen the basics of signal processing, namely signals, operators, and examples. We now set up the mathematical framework so that we can study signal processing in detail. In Module 2.1, we start very slowly by introducing intuitive geometrical notions in the real plane, or so-called R2. In Module 3.2, we present the main characters, which are vectors, norms on vectors, inner products, and basis for spaces, in particular for Hilbert spaces, which is a natural generalization of Euclidean geometry to higher dimensions. Finally, in Module 3.3, we consider approximations. Approximations are very important in signal processing, for example, for filter design, for least squares approximations, and so on. Let us get started with a review of the geometry in the plane. This is very simple geometry, as we know from grade school. It's actually called Euclidean geometry, and the key is that the ingredients, namely vectors in the plane, are an abstraction that is very useful to represent signals. And so we have an intuition from two-dimensional geometry that we can generalize and manipulate signals later on very easily. The key insight is that signals indeed are vectors. Vector geometry is a natural setting. Notions like orthogonality are very general. Now, this intuition is of course very old. It goes actually back to Greek geometry and to Euclid, and Euclid in his famed book called The Elements actually wrote down the basics of geometry more than 2000 years ago. We can see this in a beautiful facsimile copy of Euclid's Elements, and for example the Pythagorean theorem is proven in a geometric way, and this very theorem is actually called Parseval theorem. It's very important in signal processing in general. The module is split into three parts. The first one is a very lightweight introduction to signal processing seen as geometry. And that's really the Euclidean view of the world and how we try to go from that very classic view to Hilbert spaces. Module 3.2 is more formal, defining vectors, vector spaces, inner products, and finally Hilbert spaces. Module 3.3 discusses the construction of bases for Hilbert spaces, in particular orthonormal bases. Let me make just an introductory comment. So usually when we go to class and we talk about Hilbert spaces, people are sort of worried because it sounds abstract and mathematical. The goal here is to show that Hilbert spaces, which is the framework to think about signal processing, is simply a generalization of the usual Euclidean geometry that we know, the spaces we live in, the three-dimensional volumes of the physical space we inhabit, or the four-dimensional space when you add time. And so it is nothing to be scared about, nothing forbidding. It's actually something very natural. And we're going to do this by entering this field very gradually. And we first start by putting an origin here. That's a black dot. It's the origin. Then we can draw a vector, x, that has two coordinates, x0 and x1. Remember, our vectors are column vectors, so when we write this, we have to put a transpose. We can write the length of this vector, which is the distance from the origin to the tip of the vector. And that we write with these double bars to indicate the square norm. Then we can add a second vector in the plane, coordinates y0, y1. It has a length given by the norm of y. Once we have two vectors, very naturally there is an angle between the two vectors given by alpha. Okay, so that's Euclidean geometry in R2. There is a particular configuration when the vectors have a right angle. So when alpha is equal to pi over 2, sometimes this is written here with a dot or with a notation like this. This shows that the two vectors are orthogonal to each other. Now, the point we want to emphasize here is that vectors can be very general objects. So one set of vectors that is interesting, it's functions over continuous time, like here this sine wave, or another sine wave, for example, over an interval. Here it's the interval -1 to 1. And we can define a space of all the functions over this interval -1 to 1 that have a square integral. So if you square the function and you integrate it over this interval, it's going to be a finite value. And here we have two examples. So x1, which is sine of f1 of t, x2, which is sine f2 of t. And we can decide to calculate what is defined as the inner product, which is simply the product of the two functions integrated over the interval from -1 to 1. Okay? So this is a very important notion. That's the inner product between x1 and x2. What is to be noted here is that previously we had vectors in R2 with an angle alpha, with an orthogonal angle of 90 degrees. Here we have also two vectors, and the question is, can we have the same notions? Okay? And sure enough, if we multiply the two functions together, we get this red function here. And if the two frequencies, f1 and f2, are integer multiples of a fundamental harmonically related frequency, it will turn out that these two vectors, these abstract vectors x1 and x2, will also be orthogonal to each other. We're going to calculate this. Okay? So we take the product, and then we look at what is positive and what is negative, because we are going to integrate. And we sort of see that for every positive part, this one, we have a negative part. This positive part, we have a negative part. This one, we have that one. And the same here and there, here and there, here and there. And so when you take the integral between -1 and 1, the integral is going to be equal to 0. So conceptually, we have exactly the same phenomenon as the two orthogonal vectors in R2. Okay, so that's a fundamental message. Vectors are very general objects, but they still have relationships like length or norm and angles between them. And that's the magic both of Euclidean geometry and of Hilbert spaces. Okay, so once we have a space, we can define bases for this space. The simplest one is in R2. We're still in R2 here. Is an orthogonal basis with a first vector here, E0, a second vector, E1, and a right angle between the two. Any vector x can be written as a linear combination here of E0 plus a linear combination of E1. Summing together, you get the vector x. Okay? A more general basis, still in R2, is a biorthogonal basis. So we have a vector V0, a vector v1. These two basis vectors span R2, but they are not orthogonal to each other. But we can obviously write any vector x as a linear combination of v0 here plus v1. That gives us x. Okay? So what is a basis? It's a set of vectors that spans the space of interest and that is linearly independent, so it's a minimal set of vectors that span, for example, R2. In this case, it's two vectors. If we were in R3, it would be three vectors, etc. Okay, we can have sometimes too many vectors for the space. So we are still in R2, but we have now three vectors. So these guys are not linearly independent. We're going to show this just in a second. But it is clear that we can write any point in R2 as a linear combination of these vectors, because of course two of them are already enough. So certainly a third one can either be ignored or can also be helpful. Okay, now let's see that these guys are not linearly independent by actually verifying that a sum of the three vectors is actually equal to 0. So let's sum x1 plus x2 and finally minus x0, and you see that x1 plus x2 is equal to minus x0, and so we can verify this equation here. So these guys are dependent on each other, which is of course obvious because, for example, we can very well write, in this case it's x0 as a linear combination of x1 or x2, etc. Okay, so that's a case where the vectors are not linearly independent. If we have, instead of too many vectors, we have not enough vectors for the space of interest. So for example, here we have R3, three-dimensional physical space, for example, but we have only two vectors. Then we cannot hope to describe any vector in R3. We can only describe its projection onto the subspace spanned by E1 and E0 in this case. So the vector x cannot be exactly represented. We can actually only project it here to an x hat, this character here, which is the best least squares approximation of x on the subspace spanned by E0 and E1. So let me draw the subspace, which is, let's say, the horizontal plane in this case. Now, interesting questions appear when we go to spaces of infinite dimensions. So we look at the interval here of -1 to 1, which is a continuous interval, and so the intuition is that there is no finite dimensional basis that will be able to represent an arbitrary function on this interval. So let's look at the particular basis. It is built up from so-called sine x over x, or more precisely, the nth basis vector here is given by sine pi nt over n, defined on the interval -1 to 1. And we look at the summation of adding more and more of these basis vectors. So the summation goes from k is equal to 0 to capital N, so it has n plus 1 terms, and we look at the vectors with index here 2k plus 1. Okay? So when capital N is equal to 0, we have one term, it's a sine wave. Then when we go to n is equal to 1, we have two terms. We have the addition of two vectors. N is equal to 2. We have three vectors. We start to see something interesting happening. Okay, but it's still a very smooth function. N is equal to 10. We start to really see what will be the result, or approximately the result, which is a so-called square wave. So something that will be close to -1, close to +1, and has a transition here around the origin. Okay, so that's for n is equal to 10. N is equal to 50. Well, it looks more and more like the square wave, but it has these little wiggles, okay, in particular at the points of discontinuity. Okay, and n is equal to 150. It looks, you know, very close to the square wave, except at the boundary. So we see here something very particular happening. It's called non-uniform convergence. It's a term from Fourier theory that will not investigate more, but it's something that is known also as a Gibbs phenomenon, and is an annoyance here in this approximation of this square wave or box functions by these sine waves.